we believe that we are going to a more autonomous world. So this, I think in the next 5 years, this more accurate positioning with all these other new functionalities together, connectivity, availability, and so on, will make a more digital and autonomous world.
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. In this week's podcast episode, you're going to hear from Edward Escalona. Edward is a marketing and innovation officer at the European GNSS agency. And of course, GNSS stands for Global Navigation Satellite System. So today on the podcast, we're going to be talking about some of the innovations we've seen over the last 5 to 10 years with regards to these constellations, and of course, what that also has meant for the receivers on the ground and how the receivers have evolved as well. During the conversation, we're also going to try and explain what this means for you, why you should care, and what it's going to mean for our industry in general. Okay, let's get on with the interview. Hi Edward, welcome to the podcast. So today we're going to be talking about GNSS, Global Navigation Satellite Systems, and their evolution, what that has meant for the receivers of these satellite signals, and we're going to tie that into some user applications towards the end of the episode here. But I think before we dive into all of that great stuff, perhaps you could just give the listeners a brief sort of overview of your history. How did you get involved with global navigation satellite systems?
Hi, Daniel. Thank you for inviting me. I'm currently working as a market development innovation officer at the European GNSS agency. But my background is a little bit more diverse. Because the agency I joined only recently, 2 years ago. It was established in 2004, but it was moved later on to Prague, to Czech Republic, where it has its headquarters. Even if the agency is distributed in other European locations in Europe. But the agency itself, the main role is to take charge of the operational management of the European navigation satellites, which are EGNOS and Galileo. And among this responsibility is part of the market development that is in the work that I'm supporting and in the department where I'm working now. And in the market development of the system, so basically what we do is monitoring the market and the related technology of GNSS. We are engaging with the industry and users, mainly to raise awareness of the systems and to increase the adoption. So make people aware of how these systems can be useful and how they can use it. And not only the users, but also the industry that is involved, the downstream industry. Also, let's say the third pillar, the third action that we do is to support the industry and users to create new and innovative applications that can be supported thanks to the positioning offered by the navigation systems.
And as part of your role at GSA, you produce this technology monitoring report, I guess you could call it, and I think it comes out every second year, and it's a massive document. It's 110 pages, and it is filled with an incredible amount of information. And that's part of and this is kind of what we're basing this podcast episode on, because this is the document that talks about the evolution of these different systems that I mentioned right at the start of the episode here. And I think it would be a really good idea if we could start off by letting the listeners know what this evolution looks like in terms of the satellite systems, the satellite platforms.
Yeah, so you're right. We regularly, every 2 years, produce these two reports, the market monitoring and the technology monitoring. And with the technology monitoring, basically what we do is every 2 years, we are continuously monitoring the receivers, the technology, everything that is related to GNSS. For example, every year, we monitor more than 500 receiver models, and we are checking what's the market penetration of those receivers and how are they evolving. So we check what are the trends, the evolution of the technology, the evolution of the requirements also from the users that are using that technology. And then of course, with all these trends, there are different aspects that we're analyzing and we're updating every 2 years. And in this evolution, of course, you can see how the navigation market is evolving from different aspects. From the satellite point of view, let's say, the systems are evolving and they're getting better. For example, now we have many more constellations. Before, And many people are still not using the GNSS terminology, but they are calling GPS, which is basically the American GNSS. But now we have more constellations, more systems that are doing the same as the GPS, but are allowing many more functionalities. So now we have Galileo, which is the European navigation system, but we also have the Russian GLONASS, the Chinese Beidou, and all these are adding more evolution to the systems. And it seems that navigation systems are there for long, but this is basically happening in the last 5 years. So Galileo, for example, is there operational since 2016. But since, for example, if you compare since the year 2000, in which there were basically 40 satellites from GPS, to currently that we have, together with all these constellations, more than 100 satellites. So you can see that there is a lot of difference.
Can I just stop you there? Because I'd be really curious to know. So we've got these different satellite constellations that you're talking about. A lot more satellites, are visible in the sky today to the receivers we have. What does that mean? Can we use all of them interchangeably? Does the user perceive any difference here? I mean, it's great having more satellites, but what does it actually mean for people using it? And what does it mean for the accuracy and the precision of the locations that we can derive from these satellites?
Yeah, so it's exactly as you say. So basically, in order to derive a position, so to know your receiver, your device, where is it located, it needs at least the visibility of 4 satellites. So it's 3 satellites to calculate your position, but another extra satellite to synchronize the receiver. So the way that the satellite works is that it's sending signals telling you where it is positioned. So the receiver is calculating what is the time that it's traversing this signal, so it can know what is the distance to the satellite. So when you have many more satellites, you have more visibility of satellites. It's much easier to derive this position. So you can have better accuracy. So you can have also better availability and better continuity of this positioning. And this is very important in situations, for example, in urban canyons, is what we call when you are inside in the middle of the city, of a street of the city with tall buildings, in which then the visibility of the satellite is much more limited. So you can remember before with only one constellation and GPS, when you could only maybe see 2 or 3 satellites, and then you were losing the positioning within the city. That is now very rarely to see in devices that are supporting multi-constellation, that are supporting more than one constellation. And all these constellations are built in a way that they are compatible with each other. So all the receivers that are able to see, that are supporting different constellations, are able to compute the position using the satellites from different constellations.
And I also know that there's been some advances around the use of multi-frequency from these different satellite constellations. Can you talk to us a little bit about what multi-frequency means for the receiver or for the end user?
As I was saying before, the satellites basically send signals, broadcast signals that are captured by the receivers. These signals are using specific frequencies that are, of course, standardized, but before they're using basically one frequency, and this frequency travels space. When it travels space, it travels ionosphere, it travels the atmosphere with the different all the different layers, and this creates errors. It creates delays. And these delays at the end, they are translated to a worse accuracy, let's say. That's why before we had 5, 6, 7 meters of accuracy. Now, with their inclusion of more frequencies in the satellites, now it's quite common to have dual frequency, but even there are some more professional devices that are using triple frequency. And the usage of these frequencies, what it makes is that every time this different frequency traverses the atmosphere, it behaves differently. So even if they are sent at the same time, when they are received at the receiver, they basically are received at different times. And this helps computing the errors, some of the errors that are produced in the ionosphere. So you can correct those errors at the receiver. So that helps you to have better accuracy and better robustness. And another characteristics is, for example, when I was talking about in cities, there is the problem of having a multipath. That this is the error that happens when the signal is bounced, for example, in the ground or in buildings. So you can receive multiple copies of that signal, even if it's not a fake signal, it's the real signal from the satellites, but you receive reflections of those signals, and that can complicate the computation of the position. So having multi-frequency also helps reduce this multipath errors that are received at the receiver. And there are other benefits, like having more frequencies makes the system more immune to interferences when there is other systems that are working close to a specific frequency. So if you have other frequencies, you can discard that one that is being interfered and use the other ones. So there are many benefits, and this is something that we can see more and more receivers that are supporting more frequencies, not the basic single frequency only one.
So the fact that we've got more constellations to use to take advantage of in the sky is obviously a huge benefit in terms of increasing the accuracy and the precision of the locations that we can calculate on the ground. Multi-frequencies has been a huge benefit as well. I want to stay with the idea of frequencies just for a second here, because I'm wondering what it takes to broadcast on multiple signals. Do we need to launch new satellites to do this, or can we simply reprogram the existing satellites to broadcast on multiple different frequencies using the same antennas? I'm trying to figure out the significance of this. What is the most significant breakthrough here? Is it in terms of dual frequency, that we can that it's possible to broadcast on different signals, or broadcast different signals, sorry, or is it the fact that these low-cost receivers can take advantage of the signal, of the dual frequency signal?
So the satellites, of course, you cannot use any frequency you want. You cannot add randomly frequencies and increase the number of frequencies. These have to be done by design. And obviously, these frequencies have to follow some standardization process, because they have to be certified and approved by the International Telecommunication Union. These satellites, when they are designed, because at the end, the satellite lifespan is around 10, 12 years. So these satellites are already designed with this in mind. Of course, you have to try to design them future-proof, so that new requirements and new functionalities can still be added. But in terms of frequency, these are basically pre-designed. So if you want to really, in the future, increase the number of frequencies, so you would have to make an upgrade on the satellites and change them. On the receiver side, we have seen this evolution. Originally, for example, smartphones, when they started receiving signals from the GNSS, you could only receive single frequency, and that was a problem, as we saw that of availability of the system. Now there is a huge increase on the multi-constellation and multi-frequency. In the case of smartphones, dual frequency basically is becoming a standard de facto. So all the new smartphones that are released in the market, they basically support multi-frequency, and this is what is making the breakthrough. This higher accuracy, better availability is coming to not only high-end professional devices, but also to smaller devices. This, together with the miniaturization, the smaller devices, lower consumption, is what we can see is that there are many applications that are benefiting from this higher accuracy, which before it was not an option.
Maybe now would be a really good time in the conversation to jump over and talk about what's happening on the receiver side of things. We just talked about it a little bit before, that these low-cost, low-power receivers, like what we have in our smartphones, are now capable of receiving dual frequencies and processing that, giving us a better, more accurate location. I think it might be really useful for people if we talked about receivers in different groups. Is there any way of defining these different groups of receivers? And then perhaps we could talk about how they've evolved.
So, for example, we can see three main categories. So there is the high volume devices. So these are devices like smartphones. We call them mass market or location-based systems, in which they are characterized by smaller. They have lower consumption. They are used now in more emerging markets like autonomous systems, even drones. And the evolution of these devices is what I was mentioning. Now they support the multi-constellation, so you can buy any last model of phone, even low-cost phones, are supporting several constellations and dual frequency, which is very, very important and very relevant nowadays. And what we see as well for this kind of high volume devices is that they are usually incorporating other types of sensors. So you can see this in your smartphone, in which you have inertial sensors for the movement, which can also help when you are, for example, navigate. Then the second category would be what we call the safety critical or reliability critical devices. These are devices that need assurance, need more robustness, and they are basically supporting a market that is a bit more constrained by regulations. So the evolution in terms of technology, GNSS technology, is not so strong as you could see, for example, in the high volume devices. Basically, because you need a lot of certification regulations that need to pass many layers of approval. So it's lower in adoption, but still we can see that there are already some devices that they don't require so many regulations, that they're already supporting dual frequency and multi-constellation. But the main characteristics of this type of safety critical applications and devices is that they require robustness from the system and from the position and integrity. And then there is the third group, that is what we call the high accuracy, that there are basically those devices that are used in professional environments. So they require much higher performance than the normal positioning that we would require for a normal smartphone to locate you on the street. And these are supporting basically applications like surveying, for precision agriculture, and something that they need basically centimeter accuracy or even millimeter accuracy. So they have very stringent requirements in terms of accuracy, availability, convergence times, which means the time that you make the first fix of the signal. So these devices are more advanced, they are more expensive as well, and they require external systems that are also making corrections on those errors that I said on the propagation of through the ionosphere and so on, in order to be able to compute those centimeter or decimeter accuracy. So these are, let's say, the most advanced type of devices, which they are always on the line with the innovation, and as soon as there is a new frequency, a new constellation, they always support it faster. So, but of course, they are the most expensive and they are not made for everyone.
When I listen to you talk about the evolution of some of these devices, it seems to me that the cheaper chipsets must be catching up with the more professional devices, right? We've got the dual frequency, we've talked about that, we've got multi-constellation. This is, by default in a lot of these cheaper chipsets. And we've also got onboard sensors like an IMU on a phone, for example. How blurry is that line now between these kinds of high volume devices, the cheaper chipsets, and what we might think of when we think of more professional precision devices?
Yeah, you're absolutely right, because I always use the example of the smartphone, but the smartphone has, or the telephone has become from a device that you could only call to a device that you can locate yourself, you can take photographs, you can do many other things. So it's becoming such a complex and almost professional device for several things, that this line of requirements from a professional application, sometimes there are devices that can somehow satisfy that. So we are seeing this in the miniaturization of the high accuracy devices, that there are some applications, like for example for some mapping or for asset inventory, that even you can do that with a smartphone. So you can bring that smartphone and use it for professional applications. So it's true that this line is blurring. Still, there are many limitations, like size of antennas in order to support different frequencies. The chipsets are still even if they're small and they are dual frequency, but they're not chipsets supporting triple frequencies that are now becoming more standard in more professional devices. There are things that you see that trend, that it's going to mass market, and they are kind of converging, even if of course there will be more professional features that still require a more professional device, and that cannot be satisfied by a mass market. But on that, for example, there is also a work that we are doing in Galileo, that with Android devices, that it's opening the raw measurements of GNSS, so to make them available. So you can, once you have these raw measurements, you can also compute corrections on your smartphone. Of course, the performance capability is not the same as in a professional device, but that can open for possibilities for also receiving higher accuracy. I'm talking about even decimeter accuracy to the smartphones, and not only through professional devices.
I think it's interesting that we always talk about smartphones when it's like calling a Ferrari a cup holder. Yes, they also are a phone, but they're a pretty incredible device. When you think about where they might be heading alone in terms of their ability to precisely and accurately locate us, it blows my mind each time.
That's absolutely correct. I mean, there's the new trend even in professional, that it's now called being your own device. So even you don't need professional devices, as I was mentioning, to do some professional activities. And this is smartphones have really changed this paradigm.
When you think about the evolution of GNSS, what is driving it? Is it the fact that the satellite platform shows up and says, hey, I've got a new signal, I've got a new offering, and then waits for the receivers to catch up, so the receiver's ability to process that signal to make use of it? Do they wait for them to catch up? Or is it a case where a new receiver shows up on the market and then the satellites sort of race to catch up to provide, to be able to make use of the functionality that's now available on the ground? Is there any one thing that's driving the market?
So for us, the way we work is we say we are user-centric. So basically constantly checking out the user needs. And this is basically then what it's translating to the service. So to the evolution of the service, what the user needs and how the service can satisfy those needs. And we are basically classifying these needs, I think I mentioned before, in availability, accuracy, security, and connectivity. So we see that there are many more applications and that are having more stringent requirements in terms of these different parameters. And here we are talking about future-proof systems. So we are already thinking about autonomous driving, for example, robotics, drones. You can imagine drones then flying within cities. This will need higher accuracy, higher availability, and robustness. So in terms of availability, this is somehow solved having more constellations and more satellites. In terms of accuracy, there is a bit of these, what we call democratizing the correction services. These correction services or augmentation services were first devoted only for professional segments. But now we can see this trend to move this type of corrections to mass market, to more general devices for autonomous driving, for example. But as I mentioned before, this can reach even some smartphones. We are building a new service that is called the Galileo High Accuracy Service, which will provide corrections directly from the satellites on a new frequency, and the receiver will be able to use those corrections to, let's say, correct their positioning and reach decimetric accuracy. So this is, I think, a big breakthrough. It shows how monitoring the market and monitoring these requirements, you can make some changes in the satellite to provide new services and to adapt to this evolution. There are other aspects in terms of security. There are more requirements in terms of security. What we can see is that there are more vulnerabilities of GNSS. For example, there are these methods that's called spoofing or jamming. Jamming is a way that they can scramble your signal, so you cannot receive you don't know where are you located because you don't receive the GNSS signal. There is the spoofing, on the other hand, that it can be very easily done nowadays. With simple devices, they can fake the signal of the GNSS. So you can basically receive a signal that is completely fake and it's telling you are somewhere else where you really are. And this we can see it in the news that it's happening. And on the other hand, from the satellites, what we are doing is we're trying to implement authentication systems. So this is a service that is coming soon for Galileo that's called OSNMA, Open Service Navigation Message Authentication, that is basically sending a signature message telling you and reassuring you that the GNSS signal you have received is coming actually from the satellite, from Galileo, and not from another source. This evolution of requirements is what we see that is driving at the end the market. It's driving the evolution of the receivers, and it's driving the evolution of the system itself. And of course, we are taking this into consideration when we can upgrade the current satellites, but also when we are designing the next generation of satellites that could come in 10 years' time.
I'd like to go back to what you said about authentication there and this idea of proving that you are connected to a GNSS satellite and that you're not receiving a fake signal from somewhere. Because obviously this is really important when we think about navigation. If we think about autonomous vehicles, for example, it's important that they are receiving a signal and not being sent off into a wall or in some other direction. But I'm wondering if there are not some other use cases around this in terms of perhaps payment of things, proof of location. Am I actually here when, and I can only receive things when I'm in a certain location? Are there any sort of use cases around that when we think about authentication?
So yeah, when we talk about these authentication mechanisms, it's basically to prevent the spoofing. Is what I said. Somebody that is trying to send a signal that is fake. So you can be sure that when you are computing your location, it's a real location. It's coming from the satellites. And this is very critical for safety critical applications like autonomous driving, but not only. Another example that you mentioned is the payment. So imagine that you want to pay something, and there are many systems now that are checking where you are located in order to authenticate that you are really making that payment, and it's not something fake that is trying to fake your location and do it from somewhere else. So this is very important to know exactly that you are there located. This is very important for the payment companies. Another example could be in the agricultural area, where we can see this common agricultural policy in which farmers are receiving subsidies showing how are their crops, what are they producing, and so on. And for this, they are using images and positioning showing what they are actually producing. And they need to verify that they are not faking, for example, going to the neighbor's farm to show the crops of the neighbor. So they are showing their actual crops. For the paying agencies, that is very important. So there are many use cases and in which authentication is important, and that even if we haven't heard a lot of cases of spoofing, these are increasing. Basically because the systems that are required to produce this spoofing nowadays are very, very cheap and very easy to use, basically because the GNSS signal are weak because they come from very far distance. So having a device on the ground producing the signal, you will receive a much stronger signal. So it's very easy that the receiver would take that signal instead of the actual one. So ensuring that the signal you are receiving is original, is from a trustful source, is very important.
Is this also a response to some of the ground-based networks that we see springing up? And so one of the big critiques that I've heard of GNS systems is that it's a centralized system, and it's easy to spoof the location of it. It sounds like you're working on a solution to that. But how do you see GNSS working together with some of the ground-based networks? We're already integrated in terms of the different constellations we can use. You know, there's the Russian, there's a Chinese constellation, there's the American GPS system. You know, so these constellations are integrated. They work together, and you know we can use different frequencies as well. Do you see ground-based networks also feeding into this to give a more precise and secure, I guess, location?
Yeah, I think definitely we need to go in that direction. There are, of course, other ways ground-based systems using, for example, the cellular networks. Now they are talking about location-based 5G networks, but not only telecommunications-based, and they can also be used for indoors location, for example, which is another important thing. For example, when you go inside a tunnel, that you lose the reception of GNSS, and that's a known problem. So there are systems that are built, for example, for indoors or for other ground systems, in which at the end the overall positioning system would have to take the input from all these sources. And this is very important because you will not rely only in one positioning system, but you will rely in many, which provides more robustness, provides backup in case of, for example, spoofing or jamming, or there is a failure on one of the systems. So you have all the others to rely on. And this is very important in many applications, like the one we were discussing, the autonomous driving, in which obviously there are safety critical applications in which you cannot lose the positioning if there is any autonomous system that is using the position as an input. So there are many different sources. And this hybridization of sensors and other ground systems together with GNSS is where we are going. And of course, we'll have to work together with them. So these systems are completely integrated and are understanding each other.
Could you imagine a time where GNSS was completely replaced by ground-based networks?
I think it would be risky. You could achieve higher accuracy. There are many sensors, many type of systems that can provide you positioning. For example, we now see LiDAR system based on LiDAR systems that could eventually, with the advent and the emerge of more powerful processing techniques, could become even real time, even if now it's on offline, or camera sensors in which you can check the environment, and through a 3D map that it can be compared, and it can tell you exactly where you are, where are you looking at. This is something that there are prototypes that you can already see. But these are mostly relative systems in which they locate you based on some other object, so the relation of your position with some other object. GNSS is providing you an absolute position in the Earth. And I think that is something that it's reliable, it's system proof, because it has been proved for many years that it's a very reliable system. And with improvements that it's where it's going, it's really a system that I think we are dependable on. Of course, I don't have a crystal ball and I don't know what will happen in 20, 30 years, but I think where we're going is what we mentioned, is more in the hybridization and using all these things, all these systems together, rather than making one of them disappear.
Yeah, I completely agree. Not that I'm an expert in the space at all, but it's hard to imagine that we would like fail to use or take advantage of a system like this when it's a known quantity. We're used to it, we understand it, and the global coverage side of things. I think ground-based networks sound like a really good idea, and I envision things working together in that fused sense, like what we were talking about before. But a ground-based network not going to have the global coverage that GNS has.
That's correct. So, of course, GNSS, they have satellites around the world. That is, so you can be sure that wherever you are traveling, you have visibility of satellites, so you can gather that position. If you are traveling, for example, by car, and you travel and you cross a country, if that ground-based system is mainly national, you would have to rely on agreements between different national providers to provide you a seamless transition of your position, similar to what's happening with telecommunications. So these things are adding complexity to the system. On the other hand, GNSS, it's free of charge, it's completely available, and it's global. So wherever you go, you have availability, and you can use it, and you can depend on it.
So one thing that we haven't talked about yet is the timing and synchronization application. So we're used to thinking about GNS satellites providing location, but they're also this incredible resource in terms of time, incredibly accurate clock system. Could you talk to us a little bit about some of the timing and synchronization applications and how they can be used?
GNSS systems basically produce what we call PNT, which is position, navigation, and timing. And this timing is basically because in the satellites you have very, very precise clock systems. And there are many systems in the Earth that require accurate timing for synchronizing networks, for making distribution. And there are several use cases in which GNSS timing is playing a role. For example, we see in telecommunication networks in which the synchronization of the signals, telecommunication signals and systems need precise timing for synchronizing. And of course, they can use ground systems, but eventually you need very, very precise clocks. This can provide worldwide by the satellites. There are other applications, not only telecommunications, but also, for example, in energy, where the energy distribution also has to rely on an accurate and robust synchronization system. And finally, we have the example of the finance, the stock exchange, all these financial operations. They need to be timestamped and very accurately. So you cannot make, if you make a transaction in the stock market 1 second after, you can lose a lot of money. This really needs to be very accurate. And GNSS is a very accurate source of timing and synchronization for all these applications as well.
Yeah, and once again, we get back to that idea of the global infrastructure, right? Everyone can use this. It's an open system. It doesn't require any bandwidth in terms of the internet. It's broadcast down to us, and everyone has access to it. I wonder, so we've seen a lot of change in the last 5 years in terms of GNSS systems. If you take out your crystal ball now and have a look into it, what are the next 5 years going to look like? Is there anything on the horizon which is going to completely change the system as we know it today, or revolutionize anything?
What is for sure going to happen in the next 5 years, and I think this is a very relevant breakthrough, is what I mentioned of the high accuracy service, for example, that Galileo produces, but also some other regional systems will have some corrections distributed through the satellites. For example, the new Australian S-bus will support corrections directly through the satellites, but also the Japanese QZSS with their CLAS system is also supporting corrections sent by the satellites. So this, we believe, it will be a real breakthrough, because it will, as I said before, democratize high accuracy. You will be able to accuracies up to 20 centimeters with very cheap devices, and that will open up an amount of applications and a huge range of innovation that right now we are sometimes even not foreseeing. So of course we can imagine robotics, drones, autonomous driving, but for sure there will be many other applications that once the system will be in place, they will appear. And the other system that will It's more a supporting system on the securities, what I mentioned on the authentication. It's something that is still not there. There's no other system has it. They have to rely on some other ground infrastructure, doing some other calculations. But having this functionality coming directly through the satellites, it's really simplifying things. And we believe that will also open new markets, because right now some markets that they cannot rely if on this source of positioning if it's not completely trustworthy. So once you will have this authentication put in place, they will open new markets as well, where they will be able to use GNSS systems.
So when we look 5 years out in the future, we're going to see improved navigation. We're going to see this authentication being possible in the signal itself. Is there any particular industries that stand to benefit from this, or is it just going to be universally better for every industry?
We look at the market, basically now we classify it in, for example, agriculture, in geomatics or surveying applications, in transport applications, road, rail, maritime, for navigation of vessels, for example. But what we are seeing is that the main increase in the market, in the usage of GNSS in the last years, and how we believe it will evolve, is in the mass market. So this breakthrough of having this very high accuracy and very powerful receivers of GNSS in smaller devices, so that you don't need very high-end professional devices. It's putting devices in these high volume applications like autonomous driving, and this together with other innovations of IT, for example with IoT. We can see now that more and more IoT devices also support positioning, because there are many applications in which they require to know where they are located. And also what we can see is this is not a new trend, but the cloud systems that now they're being everywhere. So the computation doesn't really need to be in the device, but it can be anywhere. All these trends together, the amount of data that all this is generating, together with feeding machine learning algorithms with artificial intelligence, we believe that we are going to a more autonomous world. So this, I think in the next 5 years, this more accurate positioning with all these other new functionalities together, connectivity, availability, and so on, will make a more digital and autonomous world. So we can already envisage some of the applications in the next 5 years, but we are sure that many more applications will arise.
Thank you very much for that. I realize that it's tricky to sort of take out the crystal ball and look into the future and make predictions, so I really appreciate that. I've just got one final question for you here, and I came across this when I was reading through the report, and I'll just read out the section for you. More than 3,700 satellites rely on GNSS to navigate in space. And I read that and I thought, well, why do satellites need to navigate in space? Aren't they on fixed orbits? Could you talk us through that?
Another area that we are working on and that we'll work on in the future, which is what is called space awareness, or situational awareness, space situational awareness, or SSA, in which you really need to track all the objects in space, all the satellites, everything what is there. Currently, there are more and more constellations, and we're not talking only about GNSS, but we are talking about many satellites providing now internet connectivity, when we are talking about mega constellations that are LEO satellites. And all these satellites, even if they are in orbit, you have to know where they are located constantly, in case the satellites move in orbit and there are some deviations in the orbits. This is very important in LEO satellites, where there is this drag from the atmosphere that they are pushing them down. So you have to correct these orbits. And you need some external source in order to be able to have accurate positioning of those satellites. So you also need a satellite system, a navigation satellite system, to locate those satellites. So yeah, this is a complex issue, but now that we are seeing more and more satellites in space, this is a very important area that also needs to be taken care of. Of course, in looking at the future, it provides more control on the debris when you want to remove satellites and you want to control where are they and so on. So it's a very important issue as well.
Edward, I really want to thank you for your time. I want to thank you for walking us through this very, very, very complex subject. I think you did an amazing job. I know that you're a little bit nervous before the interview, but you've done an amazing job, so thank you very much. So I'm going to put a link to this report that we've been talking about or referencing to during this interview in the show notes, so people can find it there. But is there anywhere else people should go if they want to learn more about GNSS?
So yeah, we have several resources. Of course, we have the our main website, which is the GSA website, gsa.europa.eu, but we have also the European GNSS Service Support website, which is the GSC, and also the EGNOS support website, in which there are tons of information related to Galileo or to EGNOS, and where you can find the official documentation of the program, of the satellite systems. There is also help desk in which you can ask questions about the services if you have any doubts. So there are many resources, and of course you can always follow our media channels in LinkedIn, Twitter, and even we are on Instagram. So many sources for getting information on GNSS.
Thanks very much, Edward. I'll put links to those resources in the show notes and people can find them from there. Thanks again. Really appreciate it.
Thank you very much, Daniel.
I really hope you enjoyed that episode. I hope you learned something new about GNSS. I just want to take a minute here just to sort of highlight a few ideas I found particularly interesting about this podcast episode. The first one being the idea that we need to prove our location, or this, I think during the episode we talked about it in terms of authentication. So proving that we were connected to a GNSS satellite and proving that that the location that we were seeing, that we were experiencing on our device was not being spoofed or altered in any way, shape or form. Edward was talking about this in terms of a GNSS solution. So somehow embedding a code, I guess, in the signal that was going to be, and using that as a form of verification that you were connected to an authoritative service like a GNSS satellite. There's a couple of other different projects out there that are trying to do the same thing, trying to sort of prove your location. And the first one I'd like to point you towards is Foam.space. And the next one is the XYO.network. So if you go to any of those two links, you'll find two different projects, but the ideas are the same. So the idea with both these is to provide a decentralized network, and a way of proving your location built on the Internet of Things. Two slightly different approaches, but if you're interested in this kind of thing, I'd recommend that you check them out. While we're on the subject of proving your location, of authentifying where you are, during a previous conversation with Edward, he mentioned this really interesting idea. At least for me, it was really interesting. And the idea was that you could secure documents by location. So set up a geofence and say this document cannot be visible outside of this location. So when we have really accurate location available to us in our everyday devices, this will mean that we can do things like this. I thought this was really interesting, and I've actually done an episode not about documents as such, but about sound. So I'll put a link in the show notes. This episode was all about making sound available at certain geolocations. So the basic idea was that you could create a tour through a city, a sightseeing tour, and you could layer sound based on the location and build up this experience, which only could be experienced as you move through a scene, as you move through a location or an area. And I thought it was a really clever idea, really interesting application, and I'll put a link in the show notes to that episode if that's something you're interested in listening to. Another thing I found really interesting and just wanted to highlight about this episode was the idea that satellites need to be able to navigate as well. So using the satellite GNSS platform to help other satellites navigate their journey through space. And I found this really great online resource. It's actually made by Esri, and it's a map of all the stuff that's orbiting our planet. So you can go and click on junk, non-junk satellites, big, small satellites, look at different orbit times, and it's actually really astounding how many things are orbiting our planet. So on the website, these things are all referred to as satellites, and there's something like, I think they've mapped 18,000 of the 19,000 things, satellites, objects, pieces of junk, whatever they are, orbiting our planet at any one time. So again, I'll put a link to this in the show notes. You can find it if you're interested. I would highly recommend checking this out. I think it's a really interesting way of showing what it is that's out there, and gives you an overview of, or at least a rough idea of how many things we have orbiting the Earth at the moment. And that's it for another episode of the Mapscaping Podcast. My name is Daniel. It's been a pleasure being your host again this week. As always, you're more than welcome to reach out to me. You can find me on social media. I'm most active on LinkedIn and Twitter at the moment. But if you want to contact me through the website, just go to mapscaping.com. You'll find an email address there, and I would really love to hear from you. Okay, we'll talk again next week. Bye.